like no one ever was. 8.2, the Pythagorean Theorem. Now you guys already know the Pythagorean Theorem, but we're going to go a little bit deeper with the Pythagorean Theorem in this chapter. Here's the reminder of the Pythagorean Theorem. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. So you guys know that as a squared plus b squared is equal to c squared. Remember the two legs, it doesn't matter which one you use for a and which one you use for b, but what does matter is the hypotenuse, the longest side. And then sometimes it's a little bit difficult to tell which side is the hypotenuse depending on how the pictures are drawn, but you can always tell from this 90 degrees. The hypotenuse side is always directly across from that 90 degrees. All right, let's do an easy example just to review how to use the Pythagorean theorem. Here I have a right triangle. I threw in some fractions to bump up the level of difficulty. But you just do a squared plus b squared is equal to c squared, and it doesn't matter which leg you use for a and which one you use for b. Square them. Remember, when adding fractions, you need a common denominator. In this case, they do have a common denominator. So you just add the numerator, and then the last step is to square root both sides. Remember, when you square root both sides, the answer is supposed to be plus and minus, but since we're dealing with lengths, we're only going to do the plus part. So the final answer is the square root of 10 over 5. You cannot square root the 10, but you can square root the 25, and that turns into a 5. All right, so that was a quick review of the Pythagorean theorem. Let's look at Pythagorean triples. So these are basically famous triangles that fit the Pythagorean theorem perfectly, like the 3, 4, 5 Pythagorean triple. It's probably the most famous one. If you use the Pythagorean theorem, it works out perfectly. 3, 4, 5. Okay, and it turns out there's a whole bunch of them. So rather than having to use the Pythagorean theorem and to solve for x, you can just use the Pythagorean triple to solve for x. So if you notice, oh, look at the 3, it became an 18. Look at the 4, it became a 24. So if you notice, you're actually multiplying the 3, 4, 5 triangle by 6. And so without having to do much work, you can figure out that if you multiply 6 to that, you'll get 30. So it's kind of like a shortcut. Instead of having to do out the whole problem, sometimes it fits the Pythagorean triple, the 3, 4, 5. And so any multiples of the 3, 4, 5 will work. Another famous Pythagorean triple is the 5, 12, 13. We don't use it as much, but I memorized it, so it's a good thing. I mean, there's only two big ones, so the 3, 4, 5, and then the 5, 12, 13. Okay? And use those to help find other ones. Let's do a Pythagorean inequality theorem. In order for three sides to make a triangle, the sum of the two smaller sides must be greater than the third side. Let's see what that means. Let's say I give you three sides. I give you three sides. One side that's 11 inches, one side that's 4 inches, and then one side that's 5 inches. The question is, if I tried to put these together, can I make a triangle? And so the theorem says you have to look at the two smaller sides. Add them up, the 4 and the 5. That's 9. According to the theorem, those two have to be bigger than the third one. Otherwise, this won't make a triangle. And in this case, 9 is not bigger than 11. So these three segments will not make a triangle. Here's what that looks like visually. See, if I tried to, You can't really, no matter how hard you try or how you put it, you will never be able to connect them. All right, so that's why the two small sides have to be bigger than the third side. Not equal. What if this were like a 6? What do you think that's going to make? A 6 and a 5 makes exactly 11. So if I had a stick that was 6 inches long, then it actually, with the 5, would make a straight line. It still would not make a triangle. So it has to be bigger than the third side. It cannot be equal. All right, so let's figure out the types of triangles. All right, so if you take A plus B, it has to be bigger than C. That's how you know you have a triangle. That's what the theorem just said. Sound effects are a little bit late, but then A squared plus B squared equals C squared. We just know that that makes a right triangle. All right, but what happens if you have A squared plus B squared is greater than C squared? When that's the case, you have what's called an acute triangle. And then, of course, oh, this is going to take a while. Can't do it. There you go. If you have A squared plus B squared is less than C squared, we have an obtuse triangle. So the first one, if you notice, there aren't any squares in it. It's just A plus B. And that has to be bigger than C. That's the first thing you check, just to see if there is a triangle or not. If that checks out, then we figure out what type of triangle using the next three. Let's do an example. What type of triangle can you make with a 6, 8, 10? Oh, if you notice, it is a Pythagorean triple. But if you didn't notice, let's see first if it makes a triangle at all. Looking at these two small ones, if you add them together, 14, it's definitely bigger than 10. So yes, this makes a triangle. Now we have to figure out what type of triangle. Let's do a squared plus b squared and c squared. A squared plus b squared gives you 36 plus 64. And it turns out that 100 equals 100. When you have an equals, we have a right triangle. Let's do this one. Let's see, if I add the two small sides, do they make a triangle? Yes, it makes a triangle because it's bigger than the 14. So now that we know that it does make a triangle, let's see what type of triangle. A squared plus b squared, something c squared. Filling in all the blanks, evaluating it. We have 221 is greater than 196. So what do we have when that's the case? An acute triangle. Let's do one more for fun. Ooh, some decimals in there. A 6, a 9.4, and a 15.5. First, we have to make sure if it's a triangle or not, adding the two small ones. Ooh, when I add these two together, they are not bigger than the third side. You get 15.4, and we needed it to be bigger than 15.5. So that means it doesn't even make a triangle, and we don't have to figure out what type, because there's no type if there's no triangle. All right, let's do some tricky ones. What about these sides? A radical 13, a 6, and a 7. Well, the first thing you have to do is figure out approximately what is radical 13. And it's about 3.6. Let's go ahead and add the two small ones together, make sure that they work out. A 3.6 with a 6 gives you a 9.6, which is much bigger than a 7. So yes, this makes a triangle. Now we have to figure out what type. Plug it into the Pythagorean formula. A squared plus b squared equals c squared. The reason why this is tricky is you have to know how to square this. The square, the little 2, cancels out the square root, and so you just have 13 left over. This one's 36, and then this one's 49. Add the left side up. You have 49 is equal to 49. What does that mean? Equals a right triangle. Last one for the day. Let's try this one. Now, a lot of students have had trouble plugging in 2 radical 3 into their calculators, and so you just have to find where the radical 3 button is and then times 2. It's approximately 3.4. When you add these two together, we have 8.4, which is bigger than the 8, which makes a triangle. Let's see what type of triangle. All right. The tricky part again is how do you square this? All right. The way you do that is you actually, the number on the outside, you square it. So 2 times 2 is 4. But this squared also cancels out that square root. So you just have a 3. So the 4 times the 3. And then the 25 comes from the 5 squared, and then the 64 comes from the 8 squared. Obviously, 3 times 4 is 8. 3 times 4 is 12. Add them together with the 25. We have 37 is less than 64, which means we have an obtuse triangle. That's it. Go ahead, try the homework. Have fun.